They didn't have to do that tonight. So my name is James Lewis, and I am the program director this year here at Mawson Lakes. But you don't really want to see me or hear me, so we're going to introduce Charley. Charley is with the Australian National University's Planetary Science Institute and holds a joint appointment as an associate professor in the Research School of Astronomy and Astrophysics and the Research School of Earth Sciences. He obtained an undergraduate degree in physics from Ludwig Maximilian Universität, Munich, Germany, and has a PhD in astrophysics from the University of California, Berkeley in 1994. He was a member of the COBE satellite team that discovered the temperature fluctuations in the cosmic microwave background. Before his appointment at ANU, he held postdoctoral positions at Strasbourg Observatory, the University of New South Wales, where he taught one of the most popular general studies courses, Are We Alone? His research areas include cosmology, exoplanetology, and astrobiology and evolutionary biology. He has about a dozen projects for students at all levels, dealing with exoplanet statistics, the recession of the moon, cosmic entropy production, and major transitions in cosmic and biological evolution and phylogenetic trees. Please join in helping me welcome Charley.
Tim, thank you. Thank you, James. Thank you. Thank you. Settle down. Thank you. So can you hear me in the back there? My mic's okay. All right, so my name is Charley Lineweaver. I'm bi-tribal, as you can tell from my accent. I'm an American and an Australian. And I'm going to talk to you today about, well, this is actually, I wanted to show you this. This is a cosmologist who drew a cartoon. And it's the universe inside out. I thought that would, you see that? And how about, and the same guy, George Gamow, he's a cosmologist, he did this cartoon. And this is his cartoon. It's his proof that the Earth cannot be a sphere. If it were a sphere, ships would fall off, the water would all fall off. That doesn't happen, therefore, it can't be a sphere. Okay, so one of the questions that I get asked, and many cosmologists get asked, is this question. This is probably the most common question. If the universe is expanding, what is it expanding into? And I'll be trying to address that question as best I can, and other questions as well. So other cosmic questions. And during this talk, please interrupt me at any time asking me, hey, Charley, I don't understand that, or that's wrong because, or wait a minute, what about blah? So just raise your hand and speak loudly. Okay. Anybody have any questions? No, I won't go yet. All right, so evidence for the Big Bang. I'm going to talk about the expansion. To do that, we have to talk about the redshift and the redshift of galaxies, because that's how the expansion of the universe was first seen by Hubble. This guy here, he's a fisherman, he's always smoking, and you're not allowed to do this anymore in an observatory. But this is in 1929, he came up with what is now called Hubble's law. So what he did was he measured the distance, he estimated the distance to a galaxy, and then he measured their velocity, and they measured their velocity by something called the redshift. So the redshift is, if you've ever gone to a car race and sat very close to the cars going by, they go, that's the sound there. So high frequency coming towards you, low frequency going away. So that's the Doppler shift with sound. And how much a shift there is depends on what fraction of the speed of sound that racing car has. Now, the same thing happens with light, but it's a little bit different. So he did this, he said, oh, look at, and parsecs, by the way, is about 3 light years, so it's 1 million parsecs, and here's 2 million parsecs, to give you the scale of the distances of the galaxies that he was looking at. So the Hubble law is pretty simple. When you have a relationship like this, it's a straight line. When you have a straight line, there's a y equals ax. So the velocity is y equals some constant times the x-axis, which is the distance. H is the constant. It's called Hubble's constant. And we've been trying to figure out what that is, because that tells you how fast the universe is expanding. But interestingly, if you know how fast it's expanding, you can put that into the past and say how long ago, how old the universe is. So if I see somebody running, if I see them running away, I can say, oh, 2 minutes ago or 2 seconds ago they were there. Another 2 seconds ago they were here. And I can figure out when they were on top of me. And when all these galaxies that are receding were on top of us, that's the age of the universe, based on the Hubble constant. So, I should point out that this is we've done much, much better since 1929. So, if this green area is what he did in 1929, that green area is right here. And we've done all of this, and the answer seems to be about 70, 72. And that's the 72 kilometers per second per megaparsec. That's the fancy way we talk about Hubble's constant. And the light year is, parsec is 3.26 light years. Okay, so that is evidence that, you could say it's evidence that we were the center of a bomb that went off and everything is moving away from us. And we're at the center of the universe. That's one explanation, but that's not a good one. We don't like that one. So there are two explanations I'm going to run through you. And one is that those galaxies are moving through space. We are here in the middle. All the galaxies we see are moving away. They're moving through space. They have velocities with respect to space. And that's this interpretation here. They start here, we're in the center, and all these things are moving away, and they're moving away. They're moving through space. That's not the right answer, but that seems kind of, well, what you would expect. Now, a second answer, which is the right answer, is that galaxies are not moving through space. They're not moving through space. But space is expanding. And that's what this diagram is supposed to show. Notice that this and this are the same, but they are arrived at very differently. These galaxies are not moving with respect to the squares. See how each galaxy is in the same place with respect to the squares? And the squares are what's getting bigger. And so the recession velocities, so galaxies have recession velocities due to the space between them expanding. It's a little bit of a subtle difference. Is everybody happy with that? Or they don't like that? So I just said they're not moving through space. The universe is expanding. That's what we mean. The space of the universe is expanding. The next question you ask is Adelaide expanding? Or is this eraser expanding? And the answer seems to be no to that. And the reason is because this thing is held together by molecular forces. Two distant galaxies are not held together by molecular forces or even gravitational forces. They're so far away that the gravitational is negligible. Then you're into Hubble flow, and then you're just moving away because space is expanding. So also, notice that this thing is like a bomb. It has a center. Also, it has an edge to it. Now, this is from a Scientific American article, and I tried to get the illustrator to do this right because I wanted to show dots everywhere here. This is a piece of the universe, a tiny piece, and that tiny piece is getting bigger. But I wanted those things to be spaced everywhere here. And here, it looks like there's an edge to it, just like there's an edge here. And so that distinction is not made there very well. Okay, so that's no good. The universe does not have a center, and it doesn't have an edge. Now, why is the light from the distant galaxies redshifted if the galaxies are not moving through space? Why is there a redshift associated with galaxies moving away when they're not really moving away? They're at rest locally. And the answer is that here's when a galaxy is moving through space. Here's the galaxy in yellow. It's giving off photons in all directions, let's say 4 directions. And here's the Earth, right? That's the Earth. We're looking here, and the galaxy is moving through space. When that happens, we get a Doppler effect. Why? Because it's moving away. It's just like it's the of this race car when it's moving away from you. That's what's happening here. Now, if you were in front of it, race car, you'd be hearing the high frequency. That would be blue shifted right here. And then for the sideways ones, they wouldn't be red shifted or blue shifted. Okay? That's if you're moving through space. That's the classic Doppler effect with sound and the relativistic Doppler effect with light. But here's what's going on, we think. The galaxies are not moving through space, which sets off 4 photons, and they go in every direction, and then the photon gets red because it's getting stretched with space. A photon was different from the eraser. I said the eraser was not getting bigger. Photons apparently get bigger as the universe is expanding. Why? Because I guess from one end to the other are not being held together by any molecular forces. So, I'll repeat what I just said. Doppler redshift from galaxy moving through space away from us, that's the Doppler redshift. The redshift from space expanding, galaxy is at rest with respect to space. You can see that because the galaxy here is at the same position relative to the grid behind it. So, the photon is not red at the emission, but this photon is red at the emission because the galaxy is moving through space away from us. Now, this photon is red as it expands with space, and all four of these photons get redshifted no matter which direction they're going in. Why? Because the space is expanding uniformly. No matter where you are, you will get redshifted if you're giving off photons. Here, we have one photon is redshifted, one photon going this direction is blue shifted, and two are not shifted at all. That's a significant difference between those two cases, and that's some of the reasons why we think the universe is expanding. So this is the Hubble's law. Now notice I don't say velocity here, I use the term recession velocity. So it's not a velocity with respect to space, like me here. I have a velocity with respect to space. But if this room were expanding, you would have a velocity with respect to me, I would have a velocity with respect to you. Remember, if the universe is expanding and you see a galaxy moving away really fast, you get over at this galaxy, you're moving away really fast. You have a velocity of recession that's very high. So it's symmetric that way. Okay, so recession velocity equals some constant, Hubble's constant times the distance. The profound implications of an expanding universe are this: time has a beginning. Now that's a rough pill to swallow. My dad doesn't believe this. He thinks time has to be going on forever in both directions, forward and backward. And he'll believe that until he dies, I think. But I tell him, whenever he says that, I said, Dad, if you find anything that's older and verifiably older than 13.8 billion years, you're going to get a Nobel Prize. So if anybody here is like my dad and thinks that time is just so fundamental that it cannot have a beginning, it's always there, like Newton, like most people, then you will get a Nobel Prize. All you have to do is find something that you can estimate that it's older than the universe. Interestingly, about 20 years ago, before we knew about energy, dark energy, there were objects in the universe that we thought were older than the universe. It's like having a daughter older than the mother. That doesn't make sense, and the cosmologists recognized, we're smart guys, we knew that didn't make any sense. So something had to give, and what gave was the discovery of an accelerating universe, and I'll show you why the presence of lambda, or the acceleration of the expansion, makes the universe older. It wasn't 12, it wasn't 13, it's 13.8. Okay, so time has a beginning, so that's kind of, since telescopes are time machines, now it's kind of weird to say telescopes are time machines because any visual detection is a time machine. Like I'm looking at you, right? You're about a billionth of a second. I don't see you as you are now, I see you as you were a billionth of a second ago. Why? Because light has a finite speed. Now, if you know this by looking at a track and you see somebody starting the gun, okay, they're off, and then you see the smoke, and then you hear about half a second or 2/10 of a second, depending on how far you are away from the gun, you then see the smoke. Or no, you see the smoke first, and then you hear it, right? It's just like thunder. You see lightning, and then you count. 1, 2, 3. Now, who among you know if I see lightning and I count 3 and then hear it, how far is that lightning? What's that? 1 kilometer. And he knows that because the speed of sound is 330 meters per second. So 330, add another 330, add another 330, you get 1. You get 1 kilometer. 330 meters adds up to 1,000 meters. That's 1 kilometer per 3 seconds. And I bet you know how far away there is if it's 6 seconds delay. Yes, he does. He shakes his head. So if you didn't know that, that's a very useful skill. It can tell you how far away that lightning was. And if there's no delay, you're right on top of it. Okay, so time has a beginning, and since telescopes are time machines, now the reason why telescopes are real time machines, they're not billionth of a second, they're not 1 second like looking at the moon, they're not 8 minutes like looking at the sun, they're kind of like looking at Andromeda, the nearest galaxy, about 2 million light years away. So you're seeing light from Andromeda. When you look at it today, you're seeing light that was emitted about 2 million years ago. And so if you look at, that's the nearest galaxy. Right? So all these other galaxies are millions and millions, tens and hundreds of, and even billions, tens of billions of light years away. And that's the sense in which we can look into the past. If the speed of light were infinite, then you could see now everywhere. I could see infinitely far away right now. I'd be looking at the now of that distant galaxy. But because it's not infinite, I have to wait for it, and I can only see the past of the things that are far away. Anybody have any questions about that? Okay, I've made this all perfectly clear so far. You've all accepted the idea that time might have a beginning. You've swallowed that red pill. Because that's a really dangerous pill to swallow, because what does it mean to have time have a beginning? We're still trying to figure that out. But anyway, as we get closer to the beginning, the observable universe is smaller and hotter. Remember, the whole thing we can see is moving away. In the past, it was closer and closer together. When you get about a second old, it starts to get hot. It gets a millionth of a second old, it's even hotter. A billionth of a second after the Big Bang, it's even hotter. And the temperature goes higher and higher and higher as we get closer to the Big Bang. So that's why it's called the hot Big Bang. I'll say that again. If you compress something, if you have a bicycle and you're compressing and you're bumping up the tire, right? And if you have to push really hard, it gets hot. And that's because the air molecules are coming closer together. And the same thing when you get galaxies and gas together, they get hot. So the universe was getting hot as you look back into the past. Okay, so if the universe is expanding, what is it expanding into? So I hope I've convinced you that the universe is expanding and in what sense it's expanding. But what is it expanding into is a question we always ask. Notice that this guy has a universe and he's looking outside his universe. You should remember that that crazy idea doesn't make sense. You cannot look outside of the universe. And yet that assumption makes the question, what is it expanding into, plausible. Why is that plausible? Because everything you know has a center and an outside, but the universe doesn't. There is no outside to the universe. If there is, it's called the universe. And there's no center to the universe except in the trivial sense that I'm here and my observable universe is centered on me. But if I'm over here, my observable universe is centered on me here, etc. If I'm over in Andromeda, my observable universe is centered on here. So the observable universe depends on the observer. And interestingly, it looks like the data is consistent with the universe being spatially flat, and that means it's consistent with the universe being spatially infinite. And the next question you ask is, does that mean there are an infinite number of U's in the universe? Because if the probability of U is epsilon, I multiply that times infinity, I get an infinite number. So Marshall, there's an infinite number of U in the universe if you think that your probability is epsilon. Now, most people don't like the idea of an infinite number of copies of themselves. And the way out of that is to say that you are unique, you're a set of measure 0. And then you multiply it times infinity, and you don't get infinity. But that's for mathematicians, I'll skip over that. Anyway, the idea that the universe has an edge and then on the outside is something is the problematic assumption in the question, if the universe is expanding, what is it expanding into? Okay. So usually when people try to explain the expansion of the universe, they do something like this. They have a disk, and then the disk gets bigger. So that disk is a two-dimensional surface, and obviously what's kind of crazy is the center is right there, and the edge is right there. And that's kind of, you're explaining something with the most misleading diagram you can put together. There's an outside to this universe. There it is, right here, right here, right here. And there's a center to it, right there, and right there, and right there, right? So I've just told you the universe doesn't have a center, doesn't have an outside, and there's a diagram explaining the expansion of the universe, which does have a center and does have an outside. No wonder you're confused. Let me show you another one. Here's another one. This is a scientific one. So here's the Big Bang here. Look at this. And here, I'm not sure whether this is meant to be a disk or just the ring on the surface. I can't figure that out. I know that the W map is right in the middle, so I don't know. But in any case, it's either a disk or a ring. And it has a center. Well, actually, if it's a ring, it doesn't have a center, right? But it does have an outside and an inside even. Right? Inside this ring is right here, outside is right here. So it does have an outside. And the universe doesn't have an outside, so again, this is misleading. Now, what about other ones? Here's a balloon model. You take a balloon, make it bigger and bigger and bigger. So there you have a two-dimensional surface, and you're making it bigger. Balloons have an inside, balloons have an outside, and the universe is in between those two. Now, if our universe has an inside, I don't know where it is, unless that's it. But this has a center that is outside of its space, right? If the surface of the balloon is a two-dimensional surface, which represents the three-dimensionality of our universe, it's curved, it's a closed universe, it has a center in this model. It also has an outside. That's what it's expanding into. That's why you're misled. Now here's another one. It's called the raisin bread model. Now here's raisin bread. It increases by a factor of 2. The raisins are the galaxies. They do not expand with the expansion of the universe. The dough is the space that expands. But the raisin bread is finite, therefore it has a center right there, and it has an outside to it. Two things that our universe does not have. So, so what are you to do? What's a fellow to do? What's a person to do in this case? I don't know, anybody have any answer to that? I'm just saying that every single model you have is kind of bad, except what we tried to do in this one, what we tried to do in this one was to show you, take an average patch of the universe. We're not showing the whole universe. We're taking a patch of a potentially infinite universe and then making the patch get bigger. You are not to imagine that this has an edge to it. You imagine that there's the universe, you take a patch, or it could be a three-dimensional patch, a pixel or something, a voxel, and then it will get bigger, and then the next one next to it gets bigger, and the next one gets bigger. And they're all getting bigger. Or another way to think of it is as an infinite trampoline. You think of you have an infinite trampoline, and you have galaxies on it, and then you stretch the thing. And then the galaxies get further apart. And I've put the edge to it at infinity so you don't have to think about it. And so that, I think, is the best model could come up with that's illustratable, along with this getting just a mere patch. Anybody have any questions on this? Expansion of the universe. Yes, loudly, please, loudly. We think so, yes. That's called a homogeneous and isotropic universe. That's what we assume, and the data is consistent with that, yes. Well, I would say that there's no center. If you have an infinite line, where's the center of it? There is no center. Huh? Your question here? Loudly, please. Well, our galaxy is not expanding. The galaxies are the raisins, like an eraser. It doesn't expand. It's gravitationally bound, and it does not expand with the expansion of the universe. Even Andromeda, which is 2 million light years away, is not expanding. In fact, we're coming together, and we're going to collide with Andromeda in about, I don't know, a few billion years. Is time already up or something? Oh, I see. Well, maybe I should repeat the questions. I could do that too. All right, so Pioneer is on its way to another star. It's like 40,000 years. It'll come, I don't know, within a few parsecs of another star. But it's not going to leave the galaxy. It does not have enough velocity to leave our galaxy. Some objects in the galaxy do, and they're interesting. Question?
Looking at this slide here, I'm seeing red-shifted photons from a galaxy that is actually receding from us. It's moving away from us, and then red-shifted photons from galaxies due to the universe expanding between us and that galaxy. How, when calculating or seeking to calculate Hubble's constant, how do you separate out the redshift caused by both these effects?
Well, we don't separate. The redshift is the redshift. The question is the interpretation of the redshift. And this is one interpretation of the redshift as the universe expanding. This is another interpretation of the galaxy moving away. And this one implies that we are at the center of the universe. because we look in every direction, we see galaxies moving away. This law about V of recession equals HD, it's true in that direction, true in that direction, true in that direction. You say, well, that means we're in the center of an explosion. But if that were the case, we could also see beyond this explosion. And we don't see the universe coming to an end. We wouldn't see, oh, galaxies turn off here because that was when the explosion occurred. We don't see that. That's what I meant by not seeing the outside of the universe.
But you can get additive effects where you have both occurring.
Well, you always have additive effects because galaxies are not perfectly at rest with respect to space. It's called peculiar velocity, and that is a trouble for cosmologists. We have to add it or subtract it. But those, when you get far enough away, the Hubble flow, the recession velocity, dominates those peculiar velocities.
So if telescopes are effectively time machines, that means that there is a limit to the time that we can see. So the universe does have an edge in the temporal dimension.
Yes.
So that's...
And spatial, in the sense that you're looking back in time, and when you look back in time, the universe gets so hot that you can't see further into it. For the same reason that you can't see into the sun. The sun has a photosphere. Why? Because that sun is so hot that electrons and protons are separate. It's ionized, and then that is a very good barrier to the free flowing of photons. That's what makes the sun opaque. That's what makes the photosphere. And that's pretty much the same thing that makes the universe opaque when you're looking back as far as you can. And then, whoa, what do you see? You see hot spots. That's the cosmic microwave background. I'll tell you about that in about 5 slides. Can you hand him that microphone? There it is.
I was going to ask, is there an experiment that differentiates those two scenarios?
Is there an experiment? Well, one experiment is, do you see an edge to the universe? That's one experiment I mentioned. Because if we're the center of a bomb, first of all, I guess not allowing vanity to take you too far. Because if you're vain, you think that you're at the center of the universe, and that's the only way you could see the same Hubble relation in that direction, that direction, that direction, that direction. You are the center of a bomb that has gone off 13.8 billion years ago, right? And if it goes off 13.8 billion years ago, there's no reason why we should have a hot Big Bang or a cosmic microwave background, which is the evidence that was discovered in 1964, which convinced almost everybody who was a steady stater to believe in the hot Big Bang and throw the steady state out. So that's some evidence as well. The fact that you can see the microwave background is not something you see, is not produced by a bomb that was here. Okay? Any others? Okay, moving on. Okay, so don't be confused by these diagrams. They're everywhere. Remember, if you just say to yourself, the universe doesn't have a center, and it doesn't have an outside because the data is consistent with it being flat and infinite, then these models, you say, what does that mean for this model? Well, all you have to do is make an infinite raisin bread, and you're okay. If you have an infinite loaf of raisin bread, you do not have the center of that loaf anymore, right? If it's an infinite loaf, there's no center to it. Can you say that? Everybody say that. If an infinite loaf has no center, a finite loaf does have a center, right? You with me on that? Okay, so everything you know has a center to it because everything you know is finite. Unless you're a mathematician, you play with infinite number lines. But you know, this has a center, I have a center, this room has a center, the earth has a center, the galaxy has a center. Everything that's finite has a center. But those are not the things that are expanding in the universe. Looks like it's infinite, has no center. Okay, and it also has no edge, but because the telescope is a time machine, you're looking back, and the universe is so hot you couldn't see further, and I'll show you that. Okay, so the universe is expanding. What is it expanding into? Well, what I just said was there's no outside. Notice that for this artist, there had to be an outside for this thing to expand into, right? That's what's illegal about these diagrams. Whenever you see a diagram like this, ask yourself, what is this thing going into? What is this black stuff out here? And that's important to ask that question. The universe does not have an outside. If it did, we'd just say, hey, that's part of the universe. Okay, now, the universe does not have a center. Now, these are 3 books about the Big Bang. Boom. There's a center, there's a center, there's a center. This is bad. This is bad and misleading. If you ever talk to anybody about the universe, don't use a book which uses this and that, because these are obviously bombs with centers. You cannot point to the Big Bang. The Big Bang was over there. I see it. No, you cannot do that. It was everywhere. It was in this room 13.8 billion years ago. It was everywhere. It was not in any specific location. It was all locations. And if you're talking about all locations, that's not the center, is it? So these books are all bad. Again, explosions have centers. Explosions have high pressure on the inside, low pressure on the outside. That's why they explode. And the Friedman model of general relativity says that we do not have a model like that. As a matter of fact, high pressure in general relativity makes something collapse, not expand. No. Okay, evidence for the Big Bang redshift. Now let's talk about the finite age of the oldest objects. So if you have expansion, you have a Big Bang, then you have a finite age. So how old is the universe? How do we know this? Well, here's Bishop Ussher, and he did a pretty good job of using the evidence he had available at the time. And his calculation gives 6,027. Now, this is the number that, if you're a creationist or a fundamentalist, this is the number you throw around. Remember, you have to add a new year every year to this, right? We don't do that with 13.8 because we'd have to wait like 100 million years before we'd have to add anything to it. But if you believe this, then that's how old the universe is. I have to change the slide every year, I say. If I show, seriously, it's a little bit of a pain, but anyway, some people believe that. Don't talk to those people. Okay. Age of the universe. Now, here's a plot I made, I don't know, about a decade ago about the age of the universe. And here's the sun, 4.567 billion years. GYA means billion years ago. That's the sun. Here's the disk of the galaxy. When you look at the Milky Way, this is how the age of the Milky Way. Here's the halo. The galaxy has a halo of globular clusters that are much, much older. That's right here. That's essentially the age of the oldest part of the galaxy. And here are estimates of the age of the universe. Notice they used to be 15, and sometimes they were here, and this was larger. So this is something, remember I told you that, hey, this daughter is older than the mother. And we knew something was wrong there. And now we have this 13.8. This is what you can think of with the error bar as the age. Some people quote a smaller error bar than that. I like to say, oh, you're not so sure about that. And anyway, so 13.8 is what you should say. Oh, okay, so here's Einstein, and here's Friedman, who simplified Einstein's equation for a homogeneous universe. That's a very important statement, a homogeneous universe. Then you can do the simplifications that Friedman developed. And he died in a weather balloon. He went too high and he froze and got pneumonia or something. Anyway, these are the different places the ages come from. So here's the Earth and the Sun. We get that from CAIs. These are the oldest parts of the calcium aluminum rich inclusions are the oldest rocks we've been able to date in our solar system. They're 4.56 billion years old. So and then notice the error bars there about 2 million or so. And that's really good. But that's how old the oldest fragments of anything in the universe, in the solar system are. Now that's really nothing compared to the age of the oldest parts of the galaxy disk. Now, how do we get that? Well, we get the galaxy halo. This is a globular cluster. We can measure that. We use isochrones to do that. Here's isochrones, and they depend on how old those stars are, because stars, when they get old, they burn more hydrogen, and then they have more helium in the center. Therefore, their temperature changes a little bit, and we can see, if we have a bunch of them, we can do some isochrone fitting and fit to the age of that cluster. That's how we get the ages of globular clusters. Then there's white dwarf cooling. You know, the sun is going to turn into a white dwarf. When it does that, it stops burning, and then it just cools down like an ember in a fire. And how hot that ember is tells you how long that fire, you know, if there's the sheriff in the Old West, and he comes along and finds a fire, oh, it's hot, therefore the thieves must be only half an hour ahead. And if it's cold, oh, they're gone at least a day or so. That's the same thing with white dwarfs. Okay, then you have uranium dating. Funny thing, you can also uranium date not only things in the laboratory, you can also uranium date stars, if you can get good enough resolution in your spectra to see this stuff. And that's a very large error bar here, but it's a new technique that's kind of interesting. Then comes Friedman's equations. You don't need to know what it means exactly, except that there's Hubble's constant as a function of time. There's Hubble's constant today. Here's the amount of dark energy in the universe, and here's the amount of matter. They have different dependencies on the scale factor there, and when we look at cosmic microwave background data to get what these guys are. Actually, this is the Hubble constant we get from here, And then we get these two from this type of analysis that you can do with the cosmic microwave background to get what the omega M and omega lambda are, because they change the pattern of the microwave background fluctuations. Should I ask any questions about this one? Yes? Wait 3 seconds. We got Alex coming. 3, 2, 1. Question.
Okay, quick one. Is the zero supposed to be like on the exponent of
Yes,
A?
yes, that's the exponent. That's the dependence. See, this is the scale factor.
But then is 1.
And the scale factor to the 0 is 1, so it shouldn't be there. But I wanted to show you the different dependence on the scale factor. This one has a scale factor 1 on A cubed. Why? Because things that, when you have an expansion, things get diluter due to how much space is there. If you double the amount of space, you half the amount of concentration. That's okay?
Yes. Maybe the other one I do it later, because maybe you will talk about it. But I was thinking, like, if you want to reply later, you can. I just say it. If this Big Bang was everywhere, then does it mean
Not if. The Big Bang was everywhere.
Okay.
Go ahead. If the Big Bang were everywhere.
So, since the Big Bang was everywhere.
There's a good one. There we go. You get an A.
Does it mean that before, like, there was nothing everywhere, or like? I mean. So
you use the word before. You talk about the before the Big Bang. I will address the issue of the time before the Big Bang. Now, I should say that about 5%, maybe 4% of colleagues who are studying this think that question makes sense. 95 say, no, that question doesn't make sense because of blah, 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 and I will tell you what blah, 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 blah is.
Thank you.
Okay. All right, now this is a diagram I wanted to show you, explain to you, illustrate how it is that when you have an accelerated expansion, the age of the universe is older. So here's an accelerated expansion right here. See how the disks are expanding. Here's if they're just coasting, there's no gravity. Here, if gravity, and here's really a lot of gravity, right? Here's a big crunch, big bang, big crunch. This thing's gonna go forever, but it's still decelerating. Why? Because the gravity of the universe is pulling all things everywhere together. Here you're just coasting, that's like turning off gravity. And here's where you turn on anti-gravity, and that's the universe we think we're in. When you do that to get to this size, notice that these sizes are all the same. To get to this size in an accelerating universe, it takes you longer. Why? Because you're accelerating the whole time. And the expansion rate here, it's a lot lower in the past. That's not the case for these guys. Right? Matter of fact, the expansion rate here is larger than here. The expansion rate here is large, and here it's getting smaller and smaller and smaller. Here it's small and getting larger. And that's why the distance between here and here, which is the age of the universe, is longer. And that enabled us to say that there's nothing in the universe that we have measured so far that is older than the universe. All the daughters are younger than their mothers. It's a consistency test. You can believe in that. Except if you go near a black hole and then like interstellar. Now, here's something. Here's a multiverse. I have one slide on the multiverse here. Here it is. Actually, there's two. So here's our galaxy. Here is our universe. And this thing is gigantic, but basically we have to draw it as a balloon because we have to draw it. If it's infinite, it's hard to draw. So we said, okay, let's make it finite. So let's make it a closed universe. That's what they did. And matter of fact, all the universes here are closed, but that's not necessarily the case. But to put it on a diagram with lots of balloons, that's what they had to do. So here's our universe, and we're seeing a little bit more of this all the time. And here's our mother universe and our grandmother universe. Here's our daughter universe. And if you've listened to the previous 10 minutes, what should you ask about this diagram? What's in the white? What's in the white? And that's a very good question, and I don't know the answer to. And neither does the illustrator here. Matter of fact, neither do the people who do inflation and multiverse models. I'm not sure how you would illustrate a multiverse model. I haven't even thought about that. It's the misleadingness of the Hubble expansion is so bad, I haven't even gotten to here. But we don't know if that's true or not. I should say that the best, quantum cosmologists that I know take this model of the multiverse very, very seriously. And the worst scientists that I know just say, it's no good. So you can do with that what you want. I would pay more attention to the best quantum cosmologists and take this seriously. The reason you should take it seriously, the hand-waving version is, to do the beginning of the universe, you have to combine general relativity with quantum mechanics. If you know anything about quantum mechanics, it's the study of statistics. It's all about statistics. There is no such thing as a unique event in quantum mechanics. It's all about statistics. And if we combine statistics with general relativity, we get boom, boom, boom. We get universes everywhere, and we have a multiverse. That's more or less the hand-waving version of why so many good quantum cosmologists take this model very seriously. Not all of them, but many do. And then they do something that I don't like, and then they say, well, in this universe, the speed of light was like this, and we vary these constants. And I don't think we have much justification for that, but a lot of them do that as well. And then they say, we're living in an optimal universe. Okay, so here's a Big Bang as a white hole. So here's a mother universe, and here's our universe, and we look back everywhere, we see this wormhole, which is kind of like a white hole. Here's a black hole here, time reverses a white hole, and that's what the Big Bang is, a white hole from our perspective. So it's very interesting that the time reversal of a black hole looks very much like the Big Bang. Notice in a black hole, things fall in, they can't fall out. In the Big Bang, things come out, they can't go back in. So, all right, relative abundances of light isotopes. Okay, here's what the sun is made of. This much hydrogen, this much helium, and then all these things, oxygen, carbon, all these things is 1.4% of the mass as non-hydrogen helium. We call these metals. And here is the approximate relative abundance of these elements in the sun. And I show you this because of, well, actually, you see these are like hydrogen bonds has one bond, oxygen makes two bonds, nitrogen 3, carbon 4. These are the things that are very, very important in life. And you can see hydrogen here, carbon, oxygen, and nitrogen. They are the 4 most abundant elements that form any kind of molecule. We're going to throw out helium because it doesn't make any molecules. So that might be a clue to why you are made out of HOCN. All right, so here's George Gamow, the guy who wrote those funny cartoons in the beginning, and here's Fred Hoyle. Fred Hoyle wanted to produce all of those elements inside stars. And George Gamow wanted to produce all those elements in the Big Bang. He said, I got a big hot oven here, big hot soup cooking away. I can produce all those elements in the Big Bang. Hoyle says, my hot oven is the center of massive stars. I'm going to produce all the elements there. It turns out that both are wrong and both are right. So he can talk about this ratio of hydrogen to helium. Obviously, that's the most important because they're the most abundant ones. But he was right about all these other ones being produced in the massive stars. So today there are 2 sources of these elements. One is the massive stars, and the other is the Big Bang for these and a few other light nuclei. Any questions about that? Yep. Okay. All right, Alex, way to go.
Hi, I'm a non-physicist, and
oh no.
Maybe there's a few others of us here. When I was at school, I was taught that all the elements were products of the sun, and I've just been to a lecture on gravity waves and the collision of neutron stars and black holes, and I did hear somewhere that they discovered where gold was generated through those collisions.
Right.
Now, how does that relate to what you've just said?
Okay, so I lied. So here's why I lied. The things that can be produced in a star that's burning and fusing can only produce up to iron. All of these things, yes. To produce these things, you need something more energetic. You need to give energy to it rather than get energy out. So the question is, so where did all these come from? Partially, they come from when a massive star is, well, for example, when a white dwarf accretes energy from a companion and it goes over the Chandrasekhar limit, 1.4 solar masses, it then can go boom. When it's falling in from being made out of atoms to being made out of neutrons, it can produce a lot of these things. It's kind of undoing the fusion, if you will. That's one way that a lot of these are made. So when neutron stars are formed from white dwarfs. But you heard something that's very new, and that is gravitational waves have recently detected the gravitational signature of 2 neutron stars coming together. And the reason we know so much about it is because when 2 neutron stars come together, they emit light. And people heard about this, and they showed the telescope. They pointed the telescopes at these things, got spectra, and were able to see what elements were coming out of that neutron star. Now you can imagine that when a white dwarf collapses and forms a neutron star, that's a lot of energy falling in. But when you have 2 neutron stars colliding, that's a lot of energy. That's much more energy, and that has a different elemental signature, and that's where this gold is. Where's AU here? Anybody see AU? Anyway, it's one of those. But there are several others that we think were produced by that. Now, it's a little bit more complicated than that because these elements often don't have just one source. They have multiple sources. So you can be produced by neutron-neutron star collision, but you can also be produced by white dwarf turning into a neutron star, and that's what makes it a little bit more interesting for some of these. But a couple of elements are predominantly produced by neutron-neutron stars, and that's what the big deal was about gold. Okay, so here's 2 nice plots. They're very easy. The universe is expanding. The radius of the universe is getting bigger and bigger. As it does, the temperature of the universe goes down, 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 down. The temperature of the universe today, when I say that, I mean the temperature of the cosmic microwave background radiation, which is 2.7 Kelvin. That's the temperature of the photons that fill the universe. That's what I mean by temperature of the universe. When we go back in time, it gets hotter and hotter and hotter and hotter, and this is what George Gamow was using to heat his cauldron of producing all these elements. So here's now, and we just say, we normalize this to a radius of 1 today, and here's where it was a half. Right? Here's where it was a quarter. And as you get closer and closer here, the universe gets smaller and smaller. You get closer and closer to a time, and that's why it's called the hot Big Bang. Why hot? Because the temperature is all the way up here. What's that? What's the radius? Radius is the size of the universe. And you say, what does that mean? You say, well, today I take, I don't know, let's say 100 million light years and let's call that 1. That's all. Or I could call it 1 billion light years and call that 1. It doesn't matter. I just called some large size 1, and that's actually, we say, this is that A in the equation. I showed you Friedman's equation. That's A. We say A today is 1. And then in the past, it was a half, and it's related to redshift is something that we can measure, and that's very important. Okay, so 2.7 Kelvin is right here. That's the temperature of the universe today. And that's what, and then it gets hotter in the past, hotter and hotter and hotter. And we know this, too, because when we look at redshift, distant objects that are high redshift, we can see the excitation of molecules that are consistent with a background that is hotter than 2.7. We see a background that's 10 degrees, 10 Kelvin. And I think we can go back to 20, but I'm not sure. But when you have a 20 Kelvin background instead of a 3, you have different excitations in the molecules, and with radio astronomy, you can see some of those. Matter of fact, the first guy, he could have discovered the microwave background if he had taken the CN measurement, the CN excitation that he saw. He's a Canadian fellow. Okay, so here's the cauldron. This is too complicated, but essentially, here's the temperature of the universe going from 3 billion to 1 billion to 300 million degrees. It's cooling down in this direction. Protons and neutrons are here, and then neutrons start decaying, and they get eaten up by the alpha particles right here. And so the ratio of protons to alpha particles is something we can see in stars and measure, and that's how we can determine all this plot and all this calculation. And so a lot of the light isotopes, they fit this calculation. So we can see deuterium, for example. We see alpha particles. We see, well, these are the alpha particles here. Then we see protons. So basically, it's the hydrogen to helium ratio that we can look at in stars. Before the oldest stars, because we want to look way back in the past before they had time to burn a lot of their hydrogen into helium. We want to see the primordial versions of the hydrogen to helium ratio, and that's what you have to do, look very far into the past. Okay, how about now the cosmic microwave background? This is something I did my PhD in. I did my PhD at Berkeley in 1994, and we studied the microwave background fluctuations from the Kobe satellite. So, if you look at the part of the sky, and if you look at something like this, how many of you are astronomers, by the way? Astronomers, raise your hand. Okay, a few. Now, astronomy, you're familiar with redshift. Redshift is how much something is redshifted. Now, when you look at picture like this, the Hubble Ultra Deep Field, I think it is, then you see objects that are half, redshift of a half, redshift of 1, redshift of 2, 3, 4, 5, all the way to about 10. The microwave background are the oldest photons you can see. These are the photosphere of the universe. Why is it photosphere? Because back then the universe was so hot, you didn't have neutral hydrogen, and then you had an opaque wall of electrons and protons. You can't see beyond that, just like for the same reason you can't see into the sun. So if you had eyes and you're changing your frequency from optical to microwave, this is what happens to the dark sky. Now, it's a little bit of a fudge because I've used colors. Just like every radio image you'll ever see in your life, just like much of what you'll see from the JWST, which is an infrared telescope, and they put it in colors so you can see it because you are limited to this tiny, tiny visual spectrum, right? And you don't want to limit yourself to that, but in order to show something to the public, that's what they have to do. And so that's what has been done here. This is a microwave part, a very small portion of the microwave sky, and this is a full map. What I mean by full map, you take this oval and wrap it around your head, and everywhere you see, that's the map. The map is the full sky, all 4 pi sterradians, not some of these lousy, low quality half sky maps that you get from a telescope on the ground. Right? A telescope can only see, well, that's not true. A telescope can, if you're at the equator, you can see everything, right? But most telescopes are either a little bit north, a little bit south, and they don't get the full sky. Anyway, this is from a satellite, can get the full sky. This is the galaxy, and this is the coolest spot we can see in this. So this is a cold spot in the microwave background. Remember, this whole thing is at a temperature of, well, today it's at 2.7. When it was emitted, it was like 3,000 Kelvin. Now, these are fluctuations. The difference between this and this, the hot spot and the cold spot, is about a few parts in 10 to the 5, a few parts in 10 to the 5. 10 to the minus 1 divided by 3 times 10 to the 5. So 3 times 10 to the minus 5, something like that. Anyway, it's very low, it's very small. It's like, these are very differential measurements, hard to make, and that's the full sky, and we made this in about 1992, 1993. Okay, this is the galaxy, and we can eliminate the galaxy. And I'm now going to show you the Planck map, which was made about, I don't know, about 5 years ago. And they have much better angular resolution. Our angular resolution was as big as a hand, like this. Theirs is about as big as a fingernail. So here's the Planck measurements. Now, every time a new person measures this, they choose a different color scheme. And it's really bad for somebody ought to confuse. Okay, we're going to take all the maps we have and put them in the same color scheme. Interestingly, one of the biggest arguments we had in making this was, is the red going to be cold or the red going to be hot? And George Smoot, the guy who won the Nobel Prize, said, oh, we're going to make red hot because that's what you are in showers. The red is hot, right? The blue is cold. But for an astronomer, you know that that's the wrong way. The blue stars are the hot ones, the red stars are the cool ones. So we had an argument about that. How physical we're going to get here. So, oh, this is for the public, so we're going to make the red hot. Okay, I don't know what the thoughts were about this. But they did make the bluish ones cold. You can see they're the same. See this cold spot here? You can see that cold spot is right here. You see the cold spots here? You can see that those are cold spots here. Anyway, so what are we looking at? Here's an analogy. I want to understand, this is a very profound thing to look as far back as you can. These are the oldest photons you can see. And what are you looking at? So here's the analogy, and I want you to use this analogy to understand this. Imagine if there's an infinite field, an infinite cricket pitch, infinite. Everybody has a watch. Everybody's screaming, ah, like that. And everybody's going to stop screaming at the same time. They all have watches. All right? So they're all going to stop screaming at the same time. So picture this. You're standing here and you're screaming, ah, and you stop. After 3 seconds, what are you going to hear? After 3 seconds, what are you going to hear? Screaming from a kilometer away. Exactly. A ring around you everywhere. Everybody's going to be screaming that are a kilometer away from you. After 6 seconds, what are you going to hear? Screaming from 2 kilometers away. But how? Okay, after a year, what you're going to hear? You're going to hear them, you're always going to hear screaming from a surface that is receding from you at the speed of sound. Okay? Even though they stopped at the same time you did. And that's not only true for you, that's also true, exactly the same thing is true for the guy over here and the woman over there. No matter where you are in this infinite pitch, you will still see this surface of last screaming. Now I'm going to do a trick. I'm going to replace sound with light. And the whole universe is hot. You're hot. Everybody's hot. It's really hot. And then we're going to make the universe transparent and cool things down. And what are you going to see? After 1 year, you're going to see a surface of last scattering from the microwave background, which is 1 year away, 1 light year away. After 1 second, you're going to see the surface that's 1 light second away, right? 300,000 kilometers away. You wait more, it's going to get further and further. So the microwave background, whose maps I just showed you, is from a surface that's receding at the speed of light. And we cannot see beyond it. These are the oldest photons you can see. So instead of the surface of last screaming, the scientific term is the surface of last scattering. When light scattered for the first time, and since then it's freely traveled through the universe. Any questions about this? This is my best analogy, I think. Yeah, we got a question over here? And notice that this diagram, you could do the same thing with this as the center. Any of them can be the center. And you might ask, how far can you go? Can you go 1 billion light years over there? Can you go an infinite amount of distance? Yes. I think, yes.
Yeah, I was just going to say, like, with the light receding at the speed of light.
The surface of last scattering receding at the speed of light?
Correct, yeah. Are we implying that that is the whole universe, or just what we can see, and there's not like light or other matter beyond that that just hasn't reached us because the universe is expanding faster than the speed of light?
We think there's a whole bunch of stuff beyond that. That time period, by the way, is 380,000 years after the Big Bang. It's not a second, it's not a minute, it's 380,000 years. It took that long for the universe to cool down to about 3,000 Kelvin, and that's when the universe became transparent, because that temperature was low enough so that electrons and protons could come together and stick, make hydrogen atoms, which were much less opaque to the photons.
And is that the time period of what you're saying the oldest photons are?
Yes, those are the oldest photons. They've been traveling for about 13.8 billion years. Or Big Bang plus 380,000.
Perfect, thank you.
Or I guess minus 380,000. Okay, so moving right on. So here's a picture. Here we are in the center. Here's the surface of last scattering or last screaming, whichever you want. Here people who study astronomy study galaxies that are here. Now, if you had a neutrino telescope, and we do have some neutrino telescopes, they're pretty lousy, but they're still new business. It's only about 3 decades. Japan has one of the better ones, you know, the Kamiokande 1 and Kamiokande 2. That's a neutrino telescope that was able to see, for example, the neutrinos that came from the supernova, 1987. 1987, yes. From, was it the LMC or the SMC? Anybody know? It was LMC? Okay, so in the Large Magellanic Cloud in 1987, we saw the neutrinos coming and light coming as well. And so with the reason I mention that is if we have a very sensitive neutrino telescope, we're able to look beyond this photosphere of the universe, just like a neutrino telescope can look through into the center of the sun. A neutrino telescope can see the center of the sun. Those electrons, protons, who cares? Boom, I can look right there. They're being produced at the center, and we can look at the center. Because neutrinos go through almost everything. But not everything. That's why the neutrino sphere is here when the universe was 10 to the 11. So that would be 100 billion Kelvin. That's pretty hot. And if one day, if we have very, very good Kamiokande 37, might be able to see the neutrino sphere, the farthest neutrinos we can ever see. Right now we're looking at the sun. You can see how bad a telescope that is. You can see the sun, right? And we can see supernova and not much else. But maybe if we improve that, we're going to be able to see this neutrino background. Then comes even something more exciting, and that is gravitational astronomy. Gravitons go through stuff even better than neutrinos. And if you had a graviton telescope, now right now we're seeing the collisions of black holes, right? They're very far away, but they're collisions of black holes. But we could, the Big Bang, we think, produced a lot of gravitational wave background. And if we have really, really, really good gravity wave telescopes, we could see the gravitosphere, and that's essentially the Planck time and the Planck temperature. And if you talk to a physicist, they don't like to say anything about time before the Planck time, 10 to the minus 43 seconds. It's a very small number, but we don't even think time exists at intervals smaller than that. Anyway, that's where this gravitosphere is. It's 10 to the 32 Kelvin. So, but every observer in the universe would see that. The observer over here also has this same circle. Remember, this is defined by where you are. So here is the microwave background. This is a full sky. And this map was made by the FIRAS instrument on board the Kobe satellite. And this is the DMR. This is the fluctuations in that. So this is the average temperature was this. And this, we're going to see fluctuations in about this digit. So we put another digit here, another digit here. And the fluctuations in that digit, depending on where in the sky you are, is this map. That's what we made. And in 2006, John Mather got the Nobel Prize for that map. And George Smoot got the Nobel Prize for that map. And George Smoot was my PhD as supervisor. Anyway, I wanted to tell you about the paradox of the ubiquitous grapefruit. Now, if I've told you that the universe used to be small in the past. Well, if you go smaller and smaller and smaller and smaller, at one time it was the size of a grapefruit. Now, here's the weird thing. That grapefruit is in that direction as far as you can see. And the same grapefruit is in as far as you can see in that direction. The small observable universe was visible if you look that way and visible if you look that way. How in the world does that make sense? That you can see the same grapefruit. So here's how you need to, so here we are today, and here's the past. And when you look into the past, I look in that direction, I'm looking along here. I look in that direction, I'm looking along here. And the photosphere I see is right, this map is this point and this point. And here's the Big Bang. But I see this grapefruit here and here. I see that grapefruit there and there. How does that work? Now here's the trick, it's not so difficult. It is, well, if you have a cone-shaped past light cone, the expansion of the universe has been taken out. But if you put in the expansion of the universe, your past light cone turns into a teardrop. And so when you look in that direction, they go back into the past and then they meet and you can look at the same grapefruit. That's the solution to the paradox of the ubiquitous grapefruit. How can time have a beginning? Well, Stephen Hawking presented with this problem, said, I know time, when you go really, really early, turns into I, which is the square root of -1 times time. That's clever because when you square that, you don't get t squared, you get minus t squared. Minus is the signature that you need, that's the signature of space. Time has plus usually, but if you put it, it turns into minus, so time becomes a dimension of space. And then that's what smooths off this shuttlecock and prevents you from having a singularity. So how can time have a beginning? Here's time and space. Well, when general relativity comes along, you bend time and space. You bend it a lot, and then you bend it a really lot. And then you can have no time before that. Somebody said time before it. How can you find before in this diagram? In this diagram, you say before, so it goes all the way down to 0. This diagram, see, you should put this thing here right there, and then you have no 0 time, and you can't get closer to some beginning because... And here's a picture of the... And here I wanted to show you, this is kind of cool. Usually you say, pretend that space is two-dimensional, and then you say, oh, space is bent by a black hole by producing like this. But that's kind of using a third dimension to show what you're assuming is two-dimensional. A better example is this. This is like three-dimensional space being curved by a body like this. Interestingly, if you rotate this black hole, it makes space do this, which looks a little like the cross-cutting of a snail. So it's kind of like whirls inside of whirls. You cut it, and then that's what it looks like. So that's complicated. So what caused the Big Bang? I get asked this a lot. What caused the Big Bang? And there is something in physics that doesn't have a cause. And that is, when you have a uranium nucleus, maybe you have a bunch of them. Maybe you have, I don't know, 2. And one of them decays, and the other doesn't. And you say, hey, why did that one decay and not the other one? The answer to that is, we don't know. The answer to that is, we use statistics to describe the half-life, and after the half-life is gone, half of them will be left. Which ones? Now, some philosophers think that doesn't make any sense. They like causes a lot, and they talk about hidden variables. Most scientists, or most quantum mechanics people say, no, we just have to get used to not having a cause. The reason I mention that is because the Big Bang, if you want to understand it very early, you need quantum mechanics again. And that produces this, you don't have a cause, you just have a decay. What caused that decay? Statistics. When you have statistics, then you have multiple universes popping into and out of existence all the time. So there's one other thing I want to say, and that is, here's Plato and Aristotle, and they're philosophers, and I want to say the nothing of modern physics is not the nothing of philosophy. And confusing these two nothings is what confuses a lot of people. About this, there's a book, A Universe from Nothing, and if you Google this and see interviews of Lawrence Krauss, you'll see him debating with philosophers, and they just don't, they're going like this. And they're going like this because Lawrence is a physicist. He knows about vacuum fluctuations and the nothing of modern physics. It's full of these irreducible quantum fluctuations, and that's what he's calling nothing, and that's what he's using as the origin of the universe. The philosophers say, you don't have anything. How could, that's crazy. You can't have something from nothing. Can't have something from nothing. Can't have something from nothing. So they're really going past each other. So as a physicist, I'm on Lawrence's side, and to any philosophers here, I say, your nothing does not exist. Our nothing exists, so we can prove it, we can show you, we can do many experiments to show what that nothing does. And so nothing equals irreducible quantum fluctuations. And if you're interested in this, write these things down. There's a Casimir effect, the Lamb shift, there's also dark energy, Hawking radiation. All of these things are experiments or observations associated with quantum fluctuations of the vacuum. They exist. And these things as well. I'll leave that up for 5 seconds so you can write it down in case you're interested. Because I think everybody should start studying nothing. And this is where you begin. Because 70% of the energy density of the universe is nothing. That's important. Don't study baryons. Baryons is 4.5% of the universe. The hell with chemistry. Learn vacuum fluctuations. Then you'll be talking about most of the universe. Okay, end up. This is Steven Weinberg. I like this guy a lot. He got the Nobel Prize in 1779. The more the universe seems comprehensible, the more it also seems pointless. That's what he said in the end of his book, the first 3 minutes. Now, so what this means is, you know, they start with Copernicus took the Earth out of the center, right? Everybody thought the Earth was the center, you know. And then what did Darwin do? He said, hey, we're animals. We're not just supreme beings of some kind. Then Freud says, you know, you don't even know what you're thinking about. And then here we say, you know, we're materialistic organisms. Materialistic reductionism tells you there's nothing holy or special or supernatural about a human being. Then we have, hey, the sun is in an anonymous position, you know, just anywhere. It's in the boondocks of the galaxy. And then if we live in a multiverse, I mean, that's anonymity squared. So this is disrespect for our position, and you can feel dethroned. Of course, you feel dethroned if you thought you were throned in the first place, right? So what you can also interpret this as, look, we're understanding more and more and more about our place in the universe, and isn't that great? We have increased understanding. Aren't brains great? So if you're interested in these topics, I can recommend nothing better than E.R. Harrison, who wrote this book, but also second edition, Cosmology, Science of the Universe, where you'll find something like 80% of the stuff, maybe 70% of the stuff I talked about tonight. And this is a quote from him. Every generation believes they have at last figured out the true nature of the universe. And you can tell by my confidence that I'm guilty of that. And thank you very much. I don't know who's in charge of time. Do we have time for questions, or who's deciding whether we have time for questions? So let's have some more questions, please. I love questions. You have... Yes, yes. Okay, that's not a question. We got a question over there and a question over there.
Hi. If you, for the entire model of the expansion of the universe, can you turn it around and just say that the galaxies are shrinking?
Well, if galaxies are shrinking, they wouldn't be getting further apart. Only by their radii would they be getting further apart, right?
Well, our rulers would be getting smaller too.
Well, if you want to do it with rulers, rulers. You're going to shrink the rulers too? Yeah. You have any reason why they're shrinking?
No, but I don't have.
Okay. Okay. So you're saying, isn't this a symmetric situation which you can interpret it in two ways? That's your. Okay. I'm going to wait. I'm going to answer the next question. No, here's the thing. I haven't thought about that very much. I'm trying to ask myself to think about it while I answer the next question. Yes?
Oh, it's more of a thank you than a question. I just want to say thank you because when my wife calls me good for nothing, I can say, well, actually.
Good. Your wife calls you good for nothing? Okay. Okay. So you're going to shrink atoms. That's what you want to do, shrink atoms. You want to shrink the Bohr radius. You're going to change, no, that means you have to change Planck's constant. You want to change a constant. You want to do that? Okay. So well, actually, no, there's a whole field of physics by some people who say the constants are changing. The way this is measured is that the fine structure constant, if it's changing, changes very subtly the spectrum of some isotopes that you can see in quasar absorption lines. And as a function of redshift, you're looking at what the value was, I don't know, 10, along the line, it's like 10 billion years ago, 8 billion years ago. And then you can see, are the ratios of these isotopes, which are they controlled by the same fine structure constant? And the answer seemed to be, some people say, oh, we're hoping, and they hoped, and they gave a result that it was changing, but it's gone away. And with better measurement. A guy named Michael Murphy at Swinburne. See at Swinburne? Anybody here from Swinburne? He's been looking at this with his PhD supervisor was John Webb. They have wrote a whole series of papers about this. I don't have much confidence in this, but that's the only paper I know in which they could test experimentally whether the fine structure constant was changing or not. Yes?
So it is fascinating to see how much time the scientists spend in finding the age of nothing. But time seems...
Wait, the universe is nothing. Come on. 70% of the universe is nothing.
And other things. But time is like a human invention, and it is kind of a modeling of what we don't understand. So are there other models that do not put time and space like as main parameters, but still try to make sense of all of this? Nothing.
There's an English guy who wrote a book about he had such a weird idea of what time was that I couldn't understand it, but he's very good, and I forget his name, and I will have to go back and look at my bookshelf to tell you. But a couple of people are interested in trying to reframe cosmology in a very, very fundamental way. One way would be with entropy rather than time, entropy increase. So instead of using some clock, you'd use entropy increase as your clock. But still, second law of thermodynamics say entropy will increase. Now, there's another argument that says, wait a minute, there's a Heisenberg uncertainty relationship that says delta E, delta T greater than h bar. When you have such a relationship, that means that you should have time asymmetry. Now, that means that if you take an equation of physics, anyone, and replace T with minus T, it should be okay. The problem with that is there's also a law called the second law of thermodynamics, which isn't an equality. It's a greater than or equal sign, and therefore you can't put T goes to minus T. Why? Because the entropy is always increasing. So another way to say that is that all the laws of physics are time reversible and therefore consistent with the uncertainty relationship delta E delta T is greater than h bar, except for the second law. So I'm not sure if that helps you at all, but That's what I thought of. Yeah, go ahead.
Thanks, Charlie. I've two questions. One I hope is relatively simple. You mentioned Andromeda is coming towards galaxy. Do we see...
And us coming towards it.
Yeah, yeah, correct. So do we experience a blue shift in observing that?
Yes.
As a result?
Yes.
Okay. And the other one I had was about the full sky map and the variations in the heat. And do we know why... I didn't quite understand why we can observe different fluctuations in that if it's kind of all moving.
We're not seeing temporal fluctuations. We're seeing spatial fluctuations. It's hot here, it's cool here. It's hot here, it's cool here. Yeah. They stay the same pretty much, unless you wait billions of years. But in our lifetimes of 100 years, it's going to be hot and cool and cool and hot and hot and cool. Those are fluctuations. When I say fluctuations, I mean spatially, not temporally. They're not going hot and cold like that.
Yeah, but so in terms of looking at it, it's the same. Spatially, I understand that. But do we know, like, is that because it's further away?
No. You're asking the question, why are there fluctuations? Why isn't it completely homogeneous?
Yes.
And the answer to that is quantum fluctuations. We think that during inflation, inflation is invoked to explain these quantum fluctuations. And as a matter of fact, there's a spectrum of these fluctuations. I don't know if I could draw. Anyway, if you look at the power spectrum of the microwave background, you will see here's power and here's size. Here's big size, little size, and you see it go like this. That's pretty much the main result of these CMB relationships. It's a power spectrum of those fluctuations, and we see fluctuations that match the prediction of quantum mechanics, of inflation, in fact. Some people would argue that, wait a minute, we could make that prediction without inflation, but inflation does predict the slope of the first part of that diagram, and that was a very important part of our discovery. We were measuring that slope, and now that slope, we used to say, oh, it's 1 plus or minus 0.1. Now it's like 0.96 plus or minus the second digit, a 1 in the second digit. So it's gotten much better with the Planck data because they have much finer data, much smaller error bars, but it's still consistent with inflationary models. When you hear inflationary models, you should think there were quantum fluctuations of some inflaton field in the early universe, and then the universe inflated, and then something called reheating. Now, this is kind of cool. Reheating, there was no matter in the universe, and then it dumped its energy, the vacuum, into the universe, creating a reference frame for the first time. So the universe did not have a reference frame. Right now, there's a speedometer. Well, how is that? If you travel with respect to the CMB, you see hot in front of you and cool behind you. And I guess maybe some of you might have missed it also. With this Hubble law, V recession equals HD, there is a D that will make the V equal to C. There is a distance that makes the speed of recession equal to C, the speed of light, and you can go to further distances and make them recede faster than the speed of light. And I'm sure you've been told, like so many other people, you can't go faster than the speed of light. Well, this is not velocity, this is recession velocity, and recession velocity can go as high as it wants to. As it just get further and further away, those things are receding faster than the speed of light. They're not moving. They're not moving with respect to space. It's space that's expanding, making them seem to recede that fast. Yeah? So notice a lot of the answers to these questions are quantum fluctuations. So if you want to know a little bit about that, study quantum field theory. That's something, if you want to understand the very earliest moments, and the Planck time, and inflation, and when inflation happened, and the different models of inflation, you asked the question about the quantum fluctuations. Those are important because those temperature fluctuations are over densities and under densities. And those over-densities create giant structures in the universe, and the under-densities create giant voids. Right? So those are the seeds that produced everything we know about. And is there a question here?
Yeah. I wanted to understand if we had started looking in the universe like some centuries ago or 1,000 years ago, would we have seen a lot farther in time?
No, you wouldn't see further. The universe would be a little younger, and you'd see. Now, right now, it's 13.8 billion years. If you lived 1 billion years ago, what would the age of the universe be?
Okay, 12.
It would be 12.8 billion.
But with the...
That's an interesting question. It says, why is the universe 13.8 billion years old? You know the answer to that one? No, because it took that long to find it out. Right? I'm not sure if that answers your question, but...
Yes, yes. With the gravitometer, gravitational waves,
Yes.
are we going to be able to learn more about, like, the universe as you were showing?
Oh, I mean, the detection of gravitational wave astronomy is incredible. It's just like Galileo all over again. Gravitational wave astronomy is going to be the future of astronomy in many, many ways. Neutrinos are having a hard time because it's such a hard thing to detect, but gravitational waves are I don't know, they're just so new, and looking at these black holes that we don't know very much about, we'd like to know what the mass range is, how big the biggest black hole looks like. It's like 40 billion solar masses in the black holes. And we're finding old black holes everywhere. We're learning a lot more about black holes than we knew before. Why? Because they're colliding. Sometimes one's rotating like this, one's rotating like this, and they're colliding, and then they have all different weird shapes of gravitational waves that are being seen that depend on the mass here, the relative masses here, the spin here, and how quickly they fall into each other. So I don't know, it's a really new science, and if you're interested in physics and gravitational waves and astronomy, then do it. If you don't want to study nothing.
Thank you.
Yeah. Mm-hmm. All right, thank you. Thank you very much. Thank you very much.
Thanks, everybody, for coming out tonight.